We are in the process of proving spectral theorem for a commuting finite family of self adjoint operators. We had stated two versions, one was the spectral measure version and the other one was the continuous functional calculus, and I know they are equivalent as we have done in the case of a single operator. Essentially the same proof works there as well, and we will prove the continuous functional calculus for this commuting family. We had started off, so just like the proof in the case of single operator, we started off with the Riemann sums and then we prove that those Riemann sums will converge and the limit is actually the object we want, which will give us a star homomorphism from continuous functions on this product space, right, that is minus norm aj to aj, the interclosed interval, and you take the product j equal to 1 to n, two bounded operators on a Hilbert space, right, where the important point is that the function x, now x is in this product space. So, it has n coordinates, x going to x j. So, that is the jth coordinate, that will give us the operator a j, right. We have this commuting family a 1 a 2 a n, and this can be recovered from those the coordinate functions, right, that is what we are trying to prove. Okay. So, let us start. So, recall that we had, so maybe I can show you the previous page. So, we had for f in C minus 1 1. So, we assume that there are only two operators, this was for simplicity. We also assume that norm of the operators is less than or equal to 1. So, that we can simply write minus 1 1 cross minus 1 1. You form the Riemann sums. So, that was what called phi sub m f. This is f value at L by 2 to the m, k by 2 to the m. So, we decompose each interval minus 1 1 into intervals of length 1 by 2 to the m, and then we have these projections, right. So, these projections we already know because of the L infinity functional calculus for a 1 and a 2, right. A 1 and a 2 are self adjoint bounded self adjoint operators. So, these are projections. So, we will show that the limit of phi n phi m f exists in the operator norm denoted by phi f, which will finally we will denote it by, because this is a function of a 1 and a 2, right. So, we can write f of a 1 a 2 and we will have a star homomorphism, right, that is what is going to happen. And once we prove the limit exists, these properties follow exactly like in the case of the single operator, because the phi sub m's have the same property. Okay. Phi sub m is multiplied. So, I will justify all that, and phi of f bar is the star of phi f, and phi is linear, and the operator norm is less than or equal to the L infinity norm of f. Okay. So, let us start. Let us write phi m f again, so that I can start talking about this. K L f of L by 2 to the m, k by 2 to the m. So, let me just copy it down and then we will look at it. L by 2 to the m, L plus 1 by 2 to the m. So, this is at the mth level, right, that is what you should remember, a 1 times chi k by 2 to the m, k plus 1 by 2 to the m, right. So, yeah, strictly speaking one should put a open interval there. So, that these intervals are disjoint ones, right. So, k and L will run over admissible numbers, right. So, we have seen that. Now, what you should remember is we are okay, let us draw this bit more, a little bigger, yeah. Let us draw this slightly bigger. So, I have minus 1, I have the square minus 1 1, right, cross minus 1 1. So, I will let me not write the coordinates, we have done this earlier. Each interval is divided into sub intervals of length 1 by 2 to the m, and similarly here, right. So, we have these subdivision into squares of side length 1 by 2 to the m, that is what you should remember, and for each square we chose the left hand corner, right, bottom corner coordinates. And so, essentially we have this square, and the projection associated to that square is the product of these two things. Okay. So, you should remember that they commute, because A 1 and A 2 commute. So, these projections will also commute, and the projections will add up to 1, right, because the intervals are disjoint and they add up to the whole interval minus 1 to 1. So, the projections, each projections, if I look at the projections only in A 1, if I add these ones, I am going to get the identity operator. Okay, remember that much. Then it is easy to see. Let us apply this on a vector v. So, instead of writing the whole messy expression, look at phi m v, where v is a vector in the Hilbert space. Look at phi m v norm square. Okay. So, what is this? Well, this is inner product of phi m f v with itself, phi m f with itself. So, this is the inner product. Now, the inner product, well, you have this whole expression to be plugged in here, and similarly on the other side, right. There are two such things. So, when I look at the inner product of these two vectors, well, remember that the projections have orthogonal ranges. So, recall that projections in each of the operators, right. So, projections chi L by 2 to the m, L plus 1 by 2 to the m A 1, okay, are orthogonal, right. So, are orthogonal meaning are have orthogonal range. Okay. So, have orthogonal range. Okay. That means, if I take the product of two such things, that is, so this is something we have done for single variable, and it is the same, right. So, chi L by 2 to the m, L plus 1 by 2 to the m A 1 into chi let us say j by 2 to the m comma j plus 1 by 2 to the m A 1. Okay, same operator is 0 if L is not equal to j, right, because those intervals will be disjoint. Similarly for A 2. Okay. So, you have those intervals disjoint, the product will be 0. So, now if you look at the inner product of phi m f with phi m f, you see that you have the cross terms going to 0. That means, the inner product of the cross terms will go to 0, because the ranges are orthogonal. So, only the diagonal terms will remain. So, we get that from the above. We get that if I look at phi m f v and the L 2 norm, that is the Hilbert space norm square, this will simply sum over k and L f of L by m, L by 2 to the m, k by 2 to the m modulus square, and chi of L by 2 to the m to L plus 1 by 2 to the m, this interval A 1, and okay, so I should let me write this clearly, it is A 1 there, and similarly the other one with A 2, right, the interval k by 2 to the m, k plus 1 by 2 to the m, right, acting on V. Right, remember these are projections. So, if you want, you can put a square there, but they are same, right. So, this is less than or equal to, I take the supremum of f outside. Okay. So, that is L infinity norm of f, right, the supremum norm of f, supremum over the interval minus 1 1 cross minus 1 1. So, remember f is a continuous function in two variables, right, and what remains is the sum over k L. Okay, so I should have written norm square, sorry. So, I have a norm square here. Okay. So, norm square of chi L by 2 to the m, L plus 1 by 2 to the m, A 1, right, A 1, and similarly for A 2, right. So, norm okay, multiplied by chi k by 2 to the m, k plus 1 by 2 to the m, A 2 V norm square, right. Now, these vectors, so this is what we did in the one variable case or a single operator case, except that we did not have two projections, we had only single projection, but the point is the same. These vectors are orthogonal to each other, because these projections come from disjoint squares, right. For each square L by 2 to the m, L plus 1 by 2 to the m cross k by 2 to the m, k plus 1 by 2 to the m, I have this projection which is the product, right, product in each variable. And if I change the square, even if one of the sides are same, does not matter, if the squares are different, the projections are going to be orthogonal, having orthogonal range, right, because one of them will be orthogonal to the other. And so, the vectors which appear inside the norm square are orthogonal to each other. So, I have several vectors which are orthogonal to each other, and sum of norm squares of that is same as the sum of the you take the sum first and take the norm square, right, because the vectors are orthogonal. So, this is nothing but integral the supremum norm of f summation k equal to L. So, I can put the norm square outside chi L by 2 to the m, L plus 1 by 2 to the m, A 1 times chi k by 2 to the m, k plus 1 by 2 to the m, A 2 acting on the vector v, and you take the norm square, right. So, the norm square goes outside now. Okay. Okay. So, when I take the sum of these things, so what happens to the sum of all this? If I sum with respect to only L, let us say, or only k first, if I sum with respect to k, I will be summing all the projections for A 2, and the sum of the intervals or the union of those disjoint intervals will be minus 1 to 1, and that is the identity operator, right. So, once I sum over L, I will get the identity operator in the A 2 part. So, I will have only sum over k sum over L and A 1, right, chi L by 2 to the m, L plus 1 by 2 to the m, A 1 acting on v and norm square again. But these vectors are also orthogonal, and when you sum up, you are going to get the identity operator again acting on v, right. So, you do this twice, which whatever you have done in the case of the single operator, you will see that this is simply norm v square. Okay. So, this is norm v square. Okay. So, what did we do? We started with phi m f, that is the Riemann sum, right, acting on v, that is bounded by independent of m, right. So, I have the L infinity norm of f and norm v square. Okay. Now, we want to show it is Cauchy, right. Okay. So, also if I take let us say m tilde greater than m. So, m tilde is a positive integer greater than m. So, there are two levels, right, mth level and m tilde level. Okay. So, keep that in mind. In mth level what happens? Mth level, the decomposition, what is the decomposition of this square? The square is the square minus 1 1 cross minus 1 1 is divided into sub squares, right. So, smaller squares. So, let us say sub squares of side length 1 by 2 to the m, right. So, a typical square is k by or L by 2 to the m, L plus 1 by 2 to the m cross k by 2 to the m, k plus 1 by 2 to the m, right. So, that is how the typical square would look like. Okay. Now, in the m, if m is greater than, if m tilde is greater than m, what happens to these squares? So, just like what happened in the case of single operator, an interval of length 1 by 2 to the m got divided into several smaller pieces. So, that it became of length 1 by 2 to the m tilde, right, m tilde was greater than m. Similarly, here also the square itself will get divided. So, each square, so let us see one square. Okay. So, I have L, I should write first. So, L by 2 to the m, k by 2 to the m, right. So, that is the end point here, right, at the left hand bottom corner, and here it would be L plus 1 by 2 to the m, k by 2 to the m, right, and here it would be L plus 1 by 2 to the m, k plus 1 by 2 to the m, and here it is L by 2 to the m, k plus 1 by 2 to the m, right. That is how the square looks like. And if you go to m tilde level, these squares, so this is one square in the mth level, right. So, this is one square in the mth level. Okay. In the m tilde level, this square is divided further, so that the side lengths are 1 by 2 to the m tilde, right, 1 by 2 to the m tilde. So, you can count how many times you need that, right. So, for the interval you have 2 to the m tilde minus m times you have to divide. So, that this happens, right. But so, if m tilde is greater than m, so if you keep this picture in mind, it will be very clear. If I look at phi m tilde of f minus phi m of f, okay, I want to look at the operator norm of that and say that that goes to 0 as m goes to infinity. Well, so take one square in the mth level. So, that is whatever is drawn here, but at the m tilde level this is getting further divided, right. So, if I take one square at the mth level, I can write. So, this is what we did in the one variable case, right. So, for a fixed k and L, I have f of okay. So, let us write this slightly clearly. So, I have f of L by 2 to the m, k by 2 to the m, right, into the projections. So, that is what happens with the first the phi sub m, right. So, L plus 1 by 2 to the m a 1 times chi whatever the interval a 2, right. Okay. So, I will write here for m tilde greater than m, right. So, that is the mth one piece in the summation for phi m. Okay. For m tilde, this particular square gets divided further, right. So, this becomes summation further f of well, I will use L and k again just to avoid writing more or let us write s and t. So, s by 2 to the m tilde, t by 2 to the m tilde, and chi s by 2 to the m tilde, s plus 1 by 2 to the m tilde, a 1, and similarly something, right, appropriate intervals. Now, you see this projection, the product of projection is the sum of these projections, right. So, I can write that projection as the sum of the projections below and with the same values of f, right. So, when I subtract, I am going to subtract f value here with f values here, but where are these guys? Remember that you had a square of length 1 by 2 to the m, and you are decomposing this into further smaller pieces, right, and the values here, they come from values of f at these points, right. For the original one you have this value. So, if I look at the difference, it is the difference of f at L by 2 to the m, k by 2 to the m, minus some value of f in that square, but the square has only size 1 by 2 to the m, right. So, clearly the operator norm, because whatever is remaining has are projections and they will add up to identity just like the single variable case. So, phi m tilde f minus phi m f, the operator norm will be less than or equal to, when I subtract, I am subtracting looking at the difference of the function value, where these points where the function is evaluated are in a small square of side length 1 by 2 to the m, right. So, I can write this as supremum mod x 1 minus y 1 less than 2 to the minus m, mod x 2 minus y 2 less than 2 to the minus m, and modulus of f of x minus f of y, right, where x is x 1 y 1, x 1 x 2, y is y 1 y 2, right. So, in the one variable case there was only one such thing and that came out, and whatever remaining added up to 1, right, because these were projections. So, these projections also add up to 1, okay, and this will go to 0. So, this is precisely where the uniform continuity is used. This goes to 0 as m goes to infinity by uniform continuity, right. So, uniform continuity of f, remember it is a continuous function on minus 1 cross minus 1, minus 1 comma 1 cross minus 1 comma 1, right, the compact set. So, once you prove that the limit exists, everything else follows as in the case of single variable, right. So, hence the limit exists, hence the limit exists, okay. So, limit m going to infinity phi m f, right. So, let us call this phi of f, okay. So, phi is linear and so phi m is, so all this I will simply write down, phi m is linear implies phi is linear, okay, that is trivial. Then if I look at phi m f star, well, what is the adjoint of phi m f? So, let us look at phi m f again. The expression for phi m f will tell me the adjoint. So, if I take the adjoint of this, the projections do not do anything, they commute, remember. So, it has no effect, taking star has no effect there, only the f becomes f bar, right. So, phi m f whole star would be phi m of f bar, right. So, that is fine, and so this implies the same property for the operator phi, right. So, the map phi, right. So, phi respects the star operation, and similarly the product, right. So, phi m of f g equal to phi m of f into phi m of g implies the same for, okay. So, I will not write down this, same for phi, right, by taking the limit. The product the homomorphism property for phi sub m comes by just looking at and taking the product, because these are projections, right. So, this is a straightforward thing, okay. So, once we have developed, so we will denote, we will denote phi f by f of a 1 a 2, okay. So, that is how we, so because we had done this for single operator f of a, right. So, similarly f of a 1 a 2, we have 2 operators, or if you have n operators you have f of a 1 a 2 a n, right, and the same proof works for n and so on, right. Okay. So, from once you have the continuous functional calculus, you know how to prove or deduce the spectral measure form, right. Once you know these things for continuous functions, you can define these measures, extend to L infinity functional calculus, right. Those steps are exactly the same way you do in the case of single operator, but let me start you off. So, exercise, prove the spectral measure version. Okay. So, prove the spectral measure version. Okay. Denote by, so phi f is denoted by f of a1 a2, right. So, what do? You have continuous functions on I will keep writing minus 1 1, it is actually minus norm a1 comma norm a1 cross the same for norm a2, right. So, instead of writing all that, I will simply write minus 1 1. Okay. So, there should not be any confusion here. We are assuming that norm a1 and norm a2 are less than or equal to 1, right. So, what we have is the continuous functional calculus. So, f here is going to f of a1 a2, and that is a star homomorphism, right, continuous star homomorphism to bounded operators on your Hilbert space. Okay. So, how do you get those measures? Remember mu, v, v and all that. So, let v belong to H, right, define the linear functional, f going to f of a1 a2 v v, right. So, that is how we define this linear functional, and modulus of f of a1 a2 acting on v inner product with v, this is less than or equal to the operator norm of f of a1 a2, which is less than or equal to the L infinity norm of f or the supremum norm of f norm v square. That tells me that this is a continuous linear functional. So, this is continuous, and so there exists a measure, right. So, implies there exists a measure mu, which we will call mu v v, right, such that f of a1 a2 v v is equal to integral over, now it is minus 1 1 cross minus 1 1 f d mu v v, right, it is etc. So, I will leave the rest to you, because you have, once you have this measure, you can define the same integral for functions which are bounded, and because the measure mu v v you can polarize that and see that it is it has all those properties you want. You will get a star homomorphism from bounded functions on minus 1 cross minus 1 1 cross minus 1 1, which is a star homomorphism, right. So, as in the single operator case, we can go to the general. So, to do all this, you start with a cyclic vector, right, to write down the version where aj's are multiplication by xj's, you start with a cyclic vector and then take the direct sum, right. So, let me write down that as well. So, as in the case of single operator, we can start with a cyclic vector, start with a vector and take the cyclic subspace, right, vector v in H, and look at the cyclic subspace generated by that, right. So, generated. So, what is the cyclic subspace generated? You look at a1 to the L1, a2 to the L2 etc. up to an to the Ln, right. You look at V where Lj are 0, 1, 2 etc. and you take the closure, right. So, this we will call. So, let us call take the vector v1 and then call h1, right. And then we have this map which takes h1 to L2 of mu v1, right. So, h1 can be identified with L2 of mu v1. So, all these are similar to what we have done in the case of single operator, and we will get that. So, we will get that the operators A1, so Aj will go to multiplication by xj. Yeah. So, then we can continue, right. So, continue to fill up the whole Hilbert space. So, continue. So, I will leave the details to you, continue to get. Okay. So, what do we get? We get a continue to get measures mu j supported in the product space, right. So, the product space j equal to 1 to n. So, I will write the general statement now, norm Aj to norm Aj, right. So, instead of minus 1 1 you have this and unitary u. So, this is a fixed unitary u such that, so the unitary will identify your Hilbert space H with L2 of this product space, but there is a direct sum, right. So, that is how we take. So, you take cyclic subspaces generated by various vectors, you have this measures and then you take the direct sum, right. So, it is direct sum j equal to 1 to, well, it could be infinity also, right. L2 of the product of these spaces, those, that is the because we have n operators norm Aj with respect to these measures, right. Okay. So, maybe I should write k there because j is already used. So, let us say mu k, right. Okay. So, this is the space. So, this is sitting inside Rn, remember that. So, we have some subset of Rn and these measures mu k supported there such that there is a unitary which identifies our Hilbert space with the direct sum of L2 and the operators Aj become multiplication by xj, right. So, that is the important part, and u Aj u inverse. So, u inverse will go from the direct sum of L2 to the Hilbert space H, and Aj takes the Hilbert space H to itself and u will take it back to the L2 space. So, uj u inverse should act on some function f in the direct sum, and I should tell you what its value is at some point x, right. Where is x? X is in the product space minus norm Aj to norm Aj. So, it has n coordinates, right. So, let me write it like that. So, at x1, x2 etcetera xn equal to, well, the jth self adjoint operator is going to be simply multiplication by xj, f of x1, x2 etcetera xn. Okay. So, we will stop here. What we just proved was, after developing the continuous functional calculus for n commuting self adjoint or bounded self adjoint operators, we just using whatever or the method we already had for a single operator case, we realize these operators as multiplication by xj's on an appropriate product space, right, L2 with respect to some measure and so on. So, this is the statement, this is the spectral theorem for a commuting family, a finite family of self adjoint operators. We will prove the same. So, in the next 2 lectures we will do the same thing for normal operators as well. So, instead of having xj, we will have zj's because we have spectrum in the complex plane and things like that. So, we will be able to identify commuting family of normal operators as multiplication by zj's on an appropriate domain. So, that is what we will do in the next class. We will stop here.